Hello everyone. So let's start phenols. After studying alcohol and ethers, you won't have trouble in studying phenols. Phenol basically are compounds which have a hydroxy group attached directly to an aromatic ring. Now that aromatic ring can be benzene. It can be substituted benzene. For instance, it can have a methyl group at any position. It can have any other alkyl group at any position. That aromatic ring need not necessarily be benzene. It can be benzene derivatives as well. It can be naphthalene. If you have a OH group on naphthalene, that is also phenol. So phenols are compounds having hydroxy group on aromatic rings. That aromatic ring can be benzene, that aromatic ring can be substituted benzene, that aromatic ring can be benzene derivatives. Now there are some important phenols that we should know. Now generally, when we say phenol, we generally mean this compound. Otherwise, by definition, phenols are all compounds having hydroxy group on aromatic ring. But generally, by phenol, we generally mean this compound. This is also called as carbolic acid. This is also called as phenic acid. Other important phenols are this is called cresol. Now this methyl is at para position, so in particular this is paracresol. You can have metacresol and orthocresol as well, depending upon the position of this methyl group with respect to this hydroxy group. If methyl group is at ortho position, this will be called as orthocresol. If it is at meta position, it will be called as metacresol. So this is a very common important phenol. We should know what cresol is. If we have 1,2-hydroxybenzene, then the name of the phenol is catechol. If that hydroxy group is at meta position, then we call it as resorcinol. If that hydroxy group, if it's 1,4-hydroxybenzene, then the name of this phenol is hydroquinone. And this one you must be knowing. It's very common, important. This is salicylic acid. Fine. This is naphthalene. If we have hydroxy group at this position, this is called 1-naphthanol. If that hydroxy group is at beta position, this is called as 2-naphthol. 1-naphthol, 2-naphthol. So these are common, very common and very important phenols. So we should know these phenols because these phenols would be coming somewhere in the course later in other chapters as well. Somebody can ask you to prepare cresol. Somebody can ask you to prepare catechol. So we must know what cresol is. We must know what catechol is. We must know generally these are bare minimum. We have to know these phenols. Now, very quickly, let's start with the method of preparation of phenols. Now, generally, by definition, we understand that these all are phenols, but generally, when we say phenol, we mean this compound. So, this carbolic acid, in particular, we are going to study how to prepare this carbolic acid. Or the term phenol will generally refer to this carbolic acid. So let's start. Method number 1 is called Dawes process. In Dawes process, we take chlorobenzene and suppose I add base to this chlorobenzene. Then we understand from the chapter of hydrocarbon, we know that nucleophilic substitution do not occur on this benzene like this, because this benzene has pi electron cloud density above and below the plane of the ring, and this base has negative charge, so that negative charge will not approach this benzene ring. Plus, there cannot be a SN2 substitution because the antibonding of this carbon is inside the ring, so no nucleophile can approach that antibonding to put its electron. So SN2 mechanism is not possible. SN1 is not possible because the cation that will be generated will be on sp hybridized carbon. So that too is not possible. So generally the substitution of this chlorobenzene is not possible. But if we make this condition of the reaction very rigorous, if we increase the temperature to around 400 degrees Celsius, if they increase the temperature to around 300 atmospheric pressure, then under these extreme conditions, the substitution does occur. And we have a phenoxide ion like this. What has happened here is the carbon to which this chlorine is attached, that is attacked by this hydroxide ion because of certain plus charge polarity, because of electronegativity difference between carbon and chlorine. When this base attacks this carbon, one of the pi bond have to shift to other carbon to create a pure plus charge on this carbon. So this carbon, which is attached to chlorine, forms a bond with this hydroxide ion, and the pi bond breaks like this. Fine. Now the aromaticity has been destroyed. Aromaticity has to be regenerated. If the reactant is aromatic, product necessarily have to be aromatic. Now aromaticity can be regenerated by the regeneration of pi bond. Pi bond can be regenerated if the Cl minus comes out. Cl minus comes out, and then this carbon gains plus charge, plus minus bond formation like this. System is basic, so hydrogen is not going to remain here. Other bases are going to come and snatch this hydrogen. So actually phenoxide ion is what we are going to have. Fine. So Dawes process is nothing but it's just fusion of sodium hydroxide with this chlorobenzene, and that will result in phenoxide ion, sodium phenoxide. And later when we protonate this sodium phenoxide, then we'll get phenol. Like this. This is an industrial method of preparation. In industries, when phenol is required in large scale, we use this process because chlorobenzene is a common organic compound. We can get it very easily. So because of abundance of chlorobenzene, the abundance of chlorobenzene actually is the importance of this reaction, because we start with chlorobenzene. This reaction is called Dawes process. Very similar to Dawes process would be if we take benzene sulfonic acid and if we do the same reaction with NaOH, then the condition don't have to be as extreme as it is in case of chlorobenzene, because in this case this sulfonic acid group is a very good leaving group, much it's a much better leaving group than chlorine. In this case, the same thing will happen. First of all, acid-base reaction will occur. It's a good acid. H plus can't remain there as it is in presence of base. So first of all, this benzene sulfonic acid is going to become benzene sulfonate. And then now the base will attack, and the whole step, the same step will occur as happened in case of chlorobenzene. Base is going to come and attack the carbon which is attached with sulfur. Now in the next steps, the sulfonate ion have to leave in order to generate aromaticity in the ring. Because it's a good leaving group, so this time the condition don't have to be as rigorous as it was in the last case. And the final product will be the same. You'll have sulfoxide ion and you'll have phenoxide ion, and after protonation that will also result in phenol. So this is simple substitution of a group by NaOH. Now this is not an easy kind of substitution that we understand, because in the chapter of hydrocarbon we studied that the substitution generally doesn't happen, but we can see that the condition of the reaction is very extreme. 300 atmospheric pressure is not a normal pressure, it's very high pressure, and the temperature is high as well. So under this extreme condition these reactions are occurring. Otherwise, because of high electron cloud density, base generally do not approach the phenyl ring. So this is the first kind of reaction that will give us phenol.